Hello, everyone. Welcome to Physics 213. This is Lab 11, which is the second lab on geometric optics. And in this particular lab, we're going to discuss a little bit about something called dispersion. And I'll talk about this in a little bit. And then also, we're going to look at lenses. So how images are formed on screens when light passes through lenses, both converging lenses and diverging lenses. They're also called double convex lenses and double concave lenses. Actually, you learned a little bit about lenses in the previous lab, in lab 10. Okay, now let me start by talking a little bit about dispersion. This was not included in the previous lab on this topic. So I added this for this semester. So I want to talk a little bit about this. And then the rest of this will be, again, I'm going to use an older video that I recorded at the beginning of the pandemic. So you will notice that some of the numbering is off a little bit, like the lab number might be slightly different, and the numbering of the questions that you're responsible for. So when we get into lenses, this numbering of these questions might be slightly different, right? But the information is all exactly the same. The other thing you'll notice is that in the video on the lenses, you're going to see that some of the information is filled in the tables. And basically that's because during the pandemic, students weren't able to collect data, weren't able to actually do the experiments. So I had to pre-collect all the data and then they just analyze the data. Okay, so just wanted to let you know that the numbering might be off a little bit, but the information is exactly the same. But since I added this new part, let me discuss a little bit about dispersion. Okay, so if you look at the definition here, basically dispersion is the separation of white light into its component colors. So if you take white light and you shine it through a glass prism, first of all, when it goes from air to glass, and then from glass back to air again, it's going to refract, right, at both surfaces. You learned this in the previous lab, in lab 10. And it turns out that the index of refraction of glass actually depends on the wavelength of the light that's passing through it. And this is given by something called Cauchy's dispersion formula. So here's the actual equation, right? It seems pretty complicated and it keeps going on for a while. So you have a constant term over lambda to the 8th and so on and so forth. But it turns out it's pretty good just to truncate this and estimate it by looking at the first two terms. And really the only thing that we're interested in here is what is the qualitative relationship between n, which is the index of refraction of the glass, and then the wavelength, lambda, the wavelength of the light passing through it. And notice here that you have an inverse relationship, right? If we increase lambda, so if we increase this value in the denominator, it's going to make n become smaller. All right, and you can see that actually in this little graph here. This is an exaggerated graph. It really only changes very slightly, but as lambda increases, n is going to decrease. Okay. So that means that since each color, remember, white light consists of light of many different wavelengths, many different colors. So each color of light has a different wavelength. This table sort of gives like the respective representative values for the wavelengths for each color of light, but it's really hard to determine like when it goes from red to orange and so on and so forth. So this is just like a representative value, sort of like in the middle of the range. So notice here, and you can tell from this table that red light has the longest wavelength and violet light has the shortest wavelength. Okay, so in this experiment, and again, if you're watching this video because you were sick or you couldn't make lab this week, make sure you get this this data and this drawing from your lab partners. So basically what you're going to do is you're going to take a ray box, so it's a light ray box that has basically emits a single ray of white light. You're going to shine it through the prism, and on a piece of paper, you're going to trace the outcoming rays of light in the different colors. You're going to exaggerate it so that we can see it more clearly. It's only a small effect, but you should see a rainbow of colors on the other side of that prism. Okay, and then based on that, there's 3 questions that you have to answer. So question 1 says, based on Snell's law, which we learned about in Lab 10, and Koichi's dispersion formula, which we just learned, and basically all you have to remember is that if wavelength increases, the index refraction through glass decreases and vice versa, right? There's an inverse relationship between n and lambda. So based on Snell's law and Koichi's dispersion formula, which color of light has the greater wavelength, red or blue? And I want you to explain that based on the picture, based on what happens when white light passes through a prism, okay? And you know the answer because I just gave it to you in the table, but you want to make sure you understand it. You want to explain why that's true. Question 2, is the index of refraction of glass the same for all wavelengths of light? Explain. Well, again, we're seeing a dispersion, right? We're seeing a rainbow pattern on the other side. So what does that tell you? Is the index refraction of glass the same for all wavelengths of light? And in question 3, I simply want you to sketch a graph that has the index refraction of glass on the y-axis, so n is on the y-axis, and the color of light is on the x-axis. So basically, if you go back to this graph that I gave you, where I did n versus lambda, you can just sketch the same exact graph, except on the x-axis, instead of lambda wavelength, you're just going to list the colors in the correct order, right? So whatever color of light goes here, which should have the shortest wavelength, and this one should have the longest, right? So this list the colors of light in the correct order. Okay, and then again, if you're watching this because you missed class, you don't have to worry about this demonstration part, but I set up some prism spectrometers in the back of the room where one of them just has white light going through, and you can see the pattern really well, the rainbow pattern really well through this spectrometer. And the other one is a spectrum that's produced by a helium gas in a discharge tube. And you'll notice if you look through the spectrometer to view the spectrum from the gas here, you're going to see like discrete wavelengths, discrete colors that appear. Okay, and it's complicated, but this in general is due to the electron energy transitions of the helium gas. But again, if you're watching this because you missed lab, don't worry about this. This was just a demonstration. Okay, and then the next part was on the lenses, when we're actually projecting an image onto a screen. And this I already pre-recorded a couple of years ago, so I will attach that next so you can get all that information. Great, thanks. So for part 5, so the double convex lens is basically a lens consisting of 2, you can see it right here, consisting of 2 convex sides, so convex, convex. And you can think of it as it's thicker in the middle, thinner at the edges. So thicker in the middle, thinner at the edges. And what should happen with a double convex lens? Well, if light comes in parallel, so I have 5 rays coming in parallel, when it hits the glass, it's going to refract. Actually, it won't go straight to the center here. I just did that because it was easier to draw it that way when I was making these. What's really going to happen, as soon as it hits the glass, it'll refract, it'll go in a straight line, and then when it goes from glass to air, it'll refract again. And it turns out if the rays are coming in parallel, they're all going to refract so that they end up passing through one single point here, and the one in the middle just goes right through. So they all intersect at this one point. This is called the focal point of that double convex or converging lens. So this would be the focal point. And then the focal length is from the center of that lens to that focal point. So that length in centimeters is from here to that focal point. Okay, now a double concave lens So I have a concave side and then a concave side. And this turns out to be a diverging lens. Parallel rays coming in, right? The one in the middle is going to go straight through. The other ones are going to refract in such a way that the rays diverge away from one another. However, if you extend these rays backwards, they all appear to come from one point. And that point that they appear to come from is the focal point of that diverging lens. So the focal length is from that focal point measured to the center of the lens. So that length in centimeters would be the focal length of that diverging lens. Now, just out of convention, the focal length for our converging lens, so again, the measurement from here, center of the lens to that focal point, is going to be a positive value. And then for a diverging lens, because the light doesn't actually meet there, it just appears to come from that point, it turns out by convention, it's a negative value for that focal length, okay? And basically the goal for this part of the experiment is to measure the focal lengths of converging and diverging lenses. Okay, so what happens now if we take a converging lens and we have some like object that's illuminated? In this case, it's going to be like an arrow. So let me show you that picture here. So we have an object, right? There's like a light source so we can see the object well. I have a converging lens, and over here I am going to have a screen so that I can focus the image onto the screen. Now, how do we know that the image is going to appear over here? Well, we can follow a couple of these rays, right? Remember, there's many, many, many different rays coming off of all parts of this object. I'm just tracking 3 of them. So the one that leaves the tip of the arrow and travels parallel, when it goes through the converging lens, remember, it's got to go through the focal point, right? So it passes through the focal point. The one that goes through the center just travels right through the center. And then the one that passes through the focal point on this side would have to emerge parallel, because if I did it backwards, if I went this way, right, parallel, it'd be refracted and would go through this particular focal point. So if I go backwards through the focal point, it's going to emerge parallel. Now, where all 3 of these rays intersect, that's got to be the tip of the arrow for the image. And notice that the image is inverted, right? So it's going to appear on the screen. When you focus on the screen, it'll appear upside down. So it's inverted. So converging lenses are going to create an inverted image here. All right, now there's a relationship between the focal length of that converging lens. So remember, that's from the center of the lens to the focal point. So that's F. And then what we call the object distance, that's from where the object was situated to the center of the lens. So I'm calling DO the object distance. And then the image distance is from the center of the lens to the screen where the image is focused, like it's focused crisply on the screen. Okay, so that would be the image distance. So what is the relationship between those 3 variables? Well, it's called the thin lens formula, and it's given right here. So it turns out that 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. Or if you just rearrange this algebraically, it's going to be easier because we're going to want to solve for F. So I just solved this for F. You can do this yourself, right? Multiply by the lowest common denominator, which is F times DO times DI, both sides. And when you rearrange it, you're going to find that F is equal to the object distance times the image distance divided by the sum of the 2, right? Divided by object distance plus image distance. This is just, they're both the same. This is just an easier formula when you're plugging in numbers, okay, if you want to find the focal length. So this is the formula, the thin lens formula, that relates those 3 variables together. All right, the other thing that we're going to want to look at is something called the magnification. Like, what does the lens do in terms of magnifying the object? So there's a couple of ways we can think about magnification. In theory, right, the magnification is simply defined to be the ratio of the image size to the object size. So what do I mean by size? I basically mean the length of that arrow, right? So if I were to measure the length of this arrow on the image and divide that by the length of the arrow from the object, that's going to be the magnification. And the negative means that it's inverted. So when the magnification is negative something, the negative just means it's flipped. The image is inverted relative to the object, okay? So that's one way of doing magnification, just simply by definition. It's the length of the image divided by the length of the object. And since it's inverted here, it's negative, whatever that ratio is. The other way you can do it is you can use these values, the object distance, DO, and the image distance. So, and again, this comes from like basic geometry, basically from similar triangles, I guess. It turns out that the magnification is equal to negative, that tells you it's inverted, and then it's just going to be the image distance divided by the object distance. So if you know this image distance, which we have from our data, and the object distance, which we have, then you can calculate the magnification that way as well. And I'm going to have you guys calculate it in both ways. Okay, what about, so that was a converging lens, right? A double convex lens. What about a diverging lens, a double concave lens? What happens here? Well, in this case, right, so here's my object, the illuminated object. I'm going to track three rays again. So one leaves the tip parallel, and when it refracts through the lens, it's going to diverge away as if, right, if you extend this backwards, it appears to be coming from the focal point of that diverging lens. It goes out. The one through the center passes right through the center. And this one's a little more confusing to me. I have to think about this a little bit. The one that would appear to go through the focal point on this side would emerge parallel. I guess that makes sense because if I came in this way parallel, right, it'd be refracted in such a way that if you extended it backwards, it would go through this focal point. So if we go from the other way, it's going to emerge parallel. Now, if I extend all these rays backwards, so dot, 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 it's all the dashed lines in this one, they intersect at one point here, and that's going to be the image of the tip of the arrow there, right? But this is not a real image. Like I can't put a screen there. I can only put a screen on this side, right? The light appears to come from there. It's not actually meeting at that point. It just appears to come from that point. Like if you look through this lens, from if your eye's over here and you look through the lens, you'll see the image there, but there's no way of putting a screen there to measure where the image is. The light is not being focused at that point. It's just appearing to come from that particular point. Okay, so that's why we call this a virtual image, right? A real image would be like this. On this side, we can put a screen there and all the light is focused on that point. So that's a real image. In this case, we have what's called a virtual image. Okay, so the problem is going to be, because we remember ultimately we want to find the focal length of this diverging lens as well. But if I can't put a screen there, how am I going to figure out the focal length of this diverging lens? Well, we're going to do, we're going to trick it a little bit. In addition to this diverging lens, we're going to put in a converging lens. Actually, it'll be the 10 centimeter converging lens. We're going to place in here. So we're going to put both lenses in together. And when you do that, you're going to get a situation like this. If I put a combination of both lenses, where I have an actual image on the other side, and I can move the screen there and focus that image. Okay, so we're going to combine the 10 centimeter converging lens with this diverging lens. Think of them as being placed together. And then we'll get a situation like this where we can figure out DO and DI. Right? And we'll use that later to find the focal length of this diverging lens. I'll explain that in a minute. Okay, so again, look at my video on how I actually collected this data. Right? You can go to that link. For the first part of the experiment, the object distance is set to be 20 centimeters from the lens. Okay, so basically what I have here in the first table is the location of the lens. I just left the lens, I had this like bench, right? And it has a meter stick on it. And I left the lens holder, which has the lens in it, at 50 centimeters. And I put the object at 30 centimeters. So that means this object distance, DO, and I filled it in for you, has to be 20, right? So that's set to be 20. Then I moved the screen, and again, you guys will see this in the video. I moved the screen so that the image was focused. And then I can take that location, right, wherever the screen is, and subtract the location of the lens, and that will be the image distance. So I'll have you guys calculate that. And then once you have that, then we can calculate the focal length of that converging lens. In fact, we actually did this for two different converging lenses. We did a 10 centimeter converging lens and a 12.5 centimeter converging lens, right? So that's lens one is a 10 centimeter one, lens two is a 12.5 centimeter one. So using the thin lens formula, you're going to calculate the focal length for both of those double convex or converging lenses. And then you want to compare what you got, your calculated value, to the accepted value of 10 and 12.5, right? By computing the 2% experimental errors. And again, show me these four calculations. Okay, then we wanted to look at the magnification. So I measured, again, and you'll see this in the video, I measured the size of the image, that arrow, with a ruler, and I got around 3.4 centimeters, right, for both of them, because that doesn't change. Then on the screen, when the screen was focused, I measured the size of the image, and I got 3.3 centimeters for the 10 centimeter converging lens, and I got 5.4 centimeters for the 12.5 centimeter converging lens. So I want you to calculate magnification two different ways. Calculate it by the definition. It's just going to be the image size divided by the object size. Okay, so you'll get those two values. And by the way, you want to put a negative there because the image was inverted in both cases. And then calculate it using the formula. Remember that formula came from basically similar triangles from geometry. So it's just negative DI divided by DO. And you have the DI and DOs from this table up here. Okay, and they should be pretty close. And again, they're going to be negative. Well, actually, in this case, the negative is built into the formula. And then compare these two by computing a percent experimental error. Now, it's a little confusing when you're subtracting with negatives here. So what I would do when you compute the percent experimental error is just compare the absolute values, right? And then divide by, let's agree that the formula is our accepted one. So subtract, find the difference, and again, just worry about their absolute values, divided by the absolute value of the formula 1 times 100, and that'll be the error. And again, show me these 6 calculations. Okay, so now the last thing we want to do for this part is determine the focal length of that diverging lens, right? The double concave diverging lens, which, remember, did not have a real image. It had a virtual image. So we had to play the little game there, and we had to first, we had to put a combination of two lenses together. We had to put the unknown diverging lens with the 10 centimeter converging lens. And once we did that, then you actually get an image on the right-hand side. So what you should do is the following. So again, if you look at my video, this is the data. So the location of the lens is at 50. Now the location of the object is at 10, right? So we set that object distance to be 40 centimeters. So I did that for you here, right? 50 minus 10. It turns out that the location of the image for that combination of the two lenses is 88. So now you can find DI, right? It'll just be the image location minus the location of the lens, right? That'll be DI. And then what you want to do first is you want to make sure you compute F combo. So this is the focal length for the combination of those two lenses. Because remember, now that the image is a real image on the right-hand side, there's going to be some focal length for that combination of the two lenses. Well, to do that, you just use the usual thin lens formula. So DO times DI, object distance, times image distance, divided by object distance plus image distance. And you have that information here, right? So compute F combo first. Then we have to use that other formula that involves the focal length if you have a combination of two lenses together. So that came from, let me go back to that for a second. I think I have it up here. Yeah. So it turns out that 1 over the focal length of the combination of the two lenses is simply equal to 1 over the focal length of the converging lens plus 1 over the focal length of the diverging lens. So to make this formula easier, because it's harder to use it when it's sort of in this inverse form, I solved this for F diverging, because that's ultimately what we want to find. So if you multiply both sides by the lowest common denominator and solve it for F diverging, you're going to get this formula. It's simply F combo times F converging divided by F converging minus F combo. Okay. So once we have F combo, this is the formula you want to use to find F diverging. So let me go back to that problem. Okay, so once we have F combo, and you got that just by using the usual standard thin lens formula, using DO and DI, then we can plug that into this formula to get our F diverging, which is what we really want. Now, what is F converging? Well, remember, we put the 10 centimeter converging lens in combination with that diverging lens. So F converging is just 10. You just have to plug in 10 here. And F combo is whatever you calculated for your F combo here. Okay, and that'll give you F diverging. And you should get something, it'll probably be like negative 20 point something or negative 21, something around that. So then compare these two by computing the percent experimental error and show me these calculations.